Hello, welcome to Greenlight, Unleashing Squid Game on GameLift. Today we're going to talk about what we learned while building and launching the backend systems for one of Netflix Game's biggest hits. This will be a technical talk for builders who are building their next great game. We are an AWS shop, so this is going to have a very strong Amazon bent, but we hope to share a few things we learned that are useful regardless of whatever platform you're on. In short, we want this to be the talk we wish you had about a year ago. I'm Rich Musser, Platform Director at Butterfield, a Netflix game studio. With me today is Butterfield, a senior server engineer on my team. Our team is responsible for building, scaling, and operating the backend systems for all of Butterfield's games. First, to answer the question you're all asking yourselves, yes, Netflix has games. Netflix got into gaming about 4 years ago and currently offers over 80 mobile titles, which are available to all Netflix members for free. We have several internal studios building exclusive games, and we have a long list of third-party titles as well. Which brings us to Squid Game Unleashed. Squid Game Unleashed is a mobile multiplayer battle royale game where up to 32 players compete in a brutal contest of twisted childhood games to be a sole survivor. Squid Game Unleashed is also the first Netflix game to be available for anyone for free. No paid membership required, so you can download and play right after this talk. We want to talk about a few things that we learned while developing this game, basically from scratch in a very short period of time. We're going to pose 3 key questions for you to consider when you're building your next title. How are you going to build it? How are you going to know it all works? And what are you going to do with the mess you make along the way? How we built it. So a little bit about how our game is put together. It's a Unity app written mostly in C# with most of the gameplay defined in a custom markup language that supports over-the-air updates. It uses a client predictive server authoritative model to protect the integrity of gameplay. Our backend is a microservice style architecture with most of the servers written in TypeScript running on Node.js. We deploy the code using Fargate Elastic Container Services and Lambdas, so it's mostly a serverless experience. DynamoDB is our primary data store, and we use Redshift for our analytics and data warehouse. Most importantly for this talk, we use GameLift for our multiplayer services. Now that Amazon has announced GameLift Streams for cloud-based gaming, we'll just be talking about GameLift servers for here. So why did we choose GameLift? We knew it would be a challenge to wrangle our global player base, get them to satisfying matches with all the other players, and deploy those servers at scale wherever those players are. We also had a fixed release date that couldn't slip since it was tied to season 2 of the TV show. And to make matters even more fun, this is our studio's first truly multiplayer live services game, so we basically had no tech to build upon. So we had to lean on GameLift to provide the solid basis for our multiplayer architecture and let us build it in a very short period of time. So here's a few terms that will help with the rest of the things we're going to be talking about today. A fleet is a group of identically configured servers managed by Amazon. You can think of it as a EC2 auto-scaling group for games. A flex match is GameLift's matchmaking solution where you can write custom matchmaking rules in JSON. A game session is the reservation of a specific game server process on a fleet that contains your players. And then dedicated server is our term for our game code that runs on the fleet instances. You can run multiple copies of your dedicated servers on each fleet instance to maximize their hardware. This shows a high-level view of our server architecture. Most of our core services run in our own VPC. Authentication, data storage, telemetry, event management, that sort of thing. Note here below the line is the infrastructure that runs on an AWS account managed by Amazon. With GameLift's managed EC2 model, you deploy your code via zip file that is then picked up by the managed services, deployed to the global regions you choose, and then spins up the servers for you. Since this code is running outside of our VPC in a only semi-trusted environment, we kind of keep it at arm's length. There are 2 primary connections between the 2 halves. The matchmaking process that hands the player off to the dedicated servers, and then a game event system that streams important game data and results back up to our systems so we can track statistics and give the players the rewards they earn during gameplay. So let's drill into matchmaking a little bit. When a player hits play on their phone, it makes a REST call to our servers, first to what we call the meta server, which is the front end for all of our microservices, which then in turn starts matchmaking on our matchmaking service. Since our platform supports multiple concurrent versions of the game, each client request includes its version number. The matchmaking service looks up that version number in a database to see what GameLift resources are tied to it, and then it issues a start matchmaking command to the Flex Match system. Once Flex Match has found a match, based on the rules you gave it, it determines which region should host that match, based upon the ping data from the client that you provided in the start matchmaking command. GameLift then reserves a free dedicated server instance, and which then fires an event on your code called onStartGameSession. Once that callback is triggered, our dedicated server initializes itself. It calls activate game session when it's ready to start accepting client requests. Once all that's done, an event is then fired from GameLift to a Lambda function we call the matchmaking processor. This in turn will notify each player in that session via WebSocket that they can now join the contest. Then once all that work is done, a match is made, a server instance is initiated, a game session is created, all the infrastructure gets out of the way, and your player's phone connects directly to the dedicated server instance, providing a very low latency connection and just letting them play our game. And here's a high-level view of our data pipeline. Data flows in from our clients and our own servers via Kinesis. That data all then goes through some custom code that enriches the data, provides a sanity check on it, and then depending on the specific event, it gets routed to one or more targets. Data to be analyzed offline, it gets sent to Redshift. We then have Tableau dashboards and reports on that data. Important operational data is then sent through CloudWatch metrics, which then have CloudWatch alarms connected to them. We have PagerDuty and Slack messages watching for those alarms. Data intended for real-time dashboards is sent to Grafana via Prometheus. And this data pipeline is key to our understanding of how if our game is actually working. We have a joke in our team that everything is a matchmaking problem. Early on, we get bugs stating that matchmaking failure on the bug title, only read the description that it was actually level 5 failed to load. Or we dig into logs and see that the servers hadn't finished deploying yet. Or the Jenkins build failed, so there are no even servers to start up. Did your phone overheat because you're playing on an unsupported potato? Well, clearly a matchmaking problem. Realize that given the complex process of getting players into and out of contests, even those on the engineering teams didn't have a common language for discussing how this actually worked and all the ways it could fail. So we created a game experience journey map. To develop that common framework of understanding the core loop of our game, we built a detailed experience journey map starting from the first time the player hits play. We mapped out each screen and all the specific technical steps that implement that. We then defined the metrics and telemetry that are emitted from each step, such as matchmaking starting, sessions created, and matchmaking error events. We track all that data in a giant data dictionary spreadsheet, and then this way we could see exactly where things went wrong so we could fix them quickly, both in QA and in production. So if we go back in time, we would have defined this much earlier to avoid lost time trying to figure out what things actually are matchmaking problems. Now, how do we make sense of all the data that's coming from this telemetry? Let's talk about observability. By default, GameLift has a pretty nice set of dashboards for monitoring your fleets. It covers the basic technical underpinnings of your infrastructure, how many players are in games, how many servers you have, how utilized your different regions are, that sort of thing. But then we realized that even with the built-in dashboards, they weren't telling us how our players are actually experiencing the game. Was there perceptible lag? Was there rubber banding? We're actually putting players into quality matches. To answer these questions, we built a series of dashboards based upon those telemetry events defined in the game experience journey. We can't go to all that here, but here's a couple of examples. To understand where our players are coming from so we can optimize our server footprint, we geolocate every player and track key metrics such as player counts and latency on a per country basis. This chart is showing an example of the number of players by country of origin. For understanding the latency to our GameLift servers, showing line charts of average latencies isn't very useful because it covers up interesting outliers, and having a screen full of 5-number summary plots can be overwhelming. Instead, we found grouping players' observed latency into bands or buckets, and then visualizing the counts of players who fall into those buckets to be much easier to understand. We could then just graph the counts of players in each bucket over time or by region, and we could see how well our matchmaking algorithm changes were working. For your game, you can define the latency ranges that yield optimal experience for your players. Then you just simply track how many players fall into those ranges without having to worry about the precise and messy details of networking data. Now, to track down the details of how to improve our game based upon all that data, we need a really powerful and logging system. So Paris will now talk a little bit about how we handle logs and the tooling we built around them.
Thanks, Rich. Here's how we figure out that things are not a matchmaking problem. GameLift provides an easy way to get logs for a specific session from the AWS console, but they're not searchable. And you need to know the game session identifier to retrieve logs. From our experience, you'll also need a way to retrieve logs when the server is crashing early and no game session identifier is available. We install and configure the CloudWatch agent to forward logs from each fleet instance. Initially, we use OpenSearch for searching through the forwarded logs, but the volume of logs was overwhelming and took down our highly provisioned cluster many times. And this is just in our dev and staging environments. For production, this wouldn't be cost-effective or scalable. Using CloudWatch log insights, we can search logs across the entire fleet for issues that telemetry doesn't show us, including when the server process is failing before a game session is created, or how many game sessions have ended in the last 5 minutes. This required no additional infrastructure to manage. When a server process starts up, we provide it with unique metadata about the process, such as region, version of the game, instance ID, hostname, and port. For key server events such as activating or ending a game session, we enrich log messages with the metadata provided at startup. And when possible, we also enrich logs with the game session ID. These details make the logs relatable to the rest of our system and give us the ability to search on the metadata and quickly see what happened to a process that was running. How we managed the mess we made. Until we got an MVP of the game running on GameLift, we didn't have a clear understanding of how to manage builds and versions for the game. For our game, a single client version can be compatible with a different fleet version, and this helps when we need to make a server-only build to fix a bug. Picking a versioning strategy early is crucial. We did not, and we had to go back and retrofit our deployments. Ensure all components in your system use a centralized method for determining which version of a GameLift resource the client should use. There are 2 GameLift resources we believe are important for naming consistently with your versioning strategy: the game session queue and the matchmaking configuration, as they will be used as the entry point to start a game with GameLift. Include a version number in the ARN or the Amazon resource name. Make it easy to construct the ARN without doing additional lookups of what version should be used. The game primarily uses Terraform for resource deployment. However, Terraform was not used for creating version GameLift resources due to the challenges associated with shared Terraform state across game versions and the complexity of managing separate workspaces for each version. We had one requirement, which was the ability to update and delete resources for a game version with no impact to other versions. In the end, we used the AWS Cloud Development Toolkit to model GameLift components, which create idempotent CloudFormation stacks for each version of the game. With this, we can confidently make changes to a game version without impacting others. Our CDK project is highly config-driven. I wanted every member on our team to have the ability to make changes without writing CDK code. Things like fleet instance types, number of processes, per fleet instance, and locations can all be updated in a config file. Since we knew we need to make rapid changes to our matchmaking rules to adjust to player behavior, we built a special deploy process to push matchmaking changes live with no interruption to player experience. During peak development times, we generated 30+ builds a day, which consumed a lot of resources and generated significant cost. A build that was a week old during rapid development cycles is likely stale and not needed anymore. We built tooling to clean up old versions of the game during development. Step functions were a good fit for identifying and orchestrating which builds to shut down and delete. We could also control the rate of how many stacks or versions were deleted, as deleting too many stacks at once encountered rate limiting. Even after a stack was deleted, we kept the original server artifact around in an S3 bucket, and we can reconstitute any build if our automatic cleanup system gets greedy and cleans it up. The full end-to-end deployment of a game client and server take time. I remember a day where one of our developers asked if I could replace the game executable on a running fleet with one he generated locally because he didn't want to go through the full cycle and wait an hour for a build. I did this once, and then he asked me again. I wanted to avoid becoming a full-time manual deployment bot, so I implemented the GameLift Anywhere fleet to work with all of our resources in the stack. Anywhere fleets allow you to define GameLift compute anywhere. In this case, it's the developer's local machine running the server process. This helped to test game features faster, skipping long deployments, and getting feedback quickly. We also spent time making it easier to generate the Anywhere fleet auth tokens for developers so they wouldn't have to use the CLI. Testing with loads higher than your expected launch volume is key to your game's success. It showed us where we needed to bolster the game. After each load test, we identified where throttling occurred in internal and GameLift APIs, and being able to search the entire fleet's logs with CloudWatch Insights was a game changer. We needed to stay open to change. A few months before launching, we tested with a high concurrency of users with a single fleet and encountered some internal errors with GameLift. We reached out to AWS, and they suggested to use multiple fleets to spread the load and prevent those errors, but waiting any longer to test would have left us without enough time to make this switch. The lesson, test early and often and at scale. We learned quite a few lessons when preparing to go live with this game, and I wish we could share them all, but here are a few that we wish we knew sooner. Our internal tools focus on providing a version-centric view of game resources. To improve efficiency, it's beneficial to cache GameLift API responses wherever possible, especially for actions like listing and describing fleets, as making these API calls frequently can be costly. Additionally, implement a strong retry mechanism to handle rate limit. Prepare a glass break method for remoting into a fleet instance. Being able to run a command like top while your game is running can show you things that telemetry might miss, like small spikes in CPU during different phases of your game. Figure out how many versions of your game you can create in an account. Make sure there are enough instance types in all the required locations to support users. And when calculating, include support for the current version as well as the next 2 versions running concurrently. For flex match rules, ensure you're getting expected matches based on the inputs you provide. Don't make assumptions. We assume that if a player's latency to a location wasn't provided when making a matchmaking request, the player wouldn't be matched to that location. That was not the case. We learned to provide latency for all locations your fleet is deployed to, and if you don't want a player matched to a location, provide a value that prohibits matching. Building games is complicated. There's a lot of interconnected decisions, and it's difficult to predict what's really important to ship. So to help guide your thinking, think about the 3 questions we posed at the beginning of this talk. How are you going to build it? How do you know it all works? How are you going to manage the mess that you make along the way? We think that answering these questions and revisiting them throughout development will help you ship your next great game. There were many great people behind building this game, so we'd like to thank everyone on the Squid Game team at Netflix, and especially highlight some of our colleagues: Travis Carson, Kyle Evans, Sean Stolberg, and Brandon Fritz. We'd also like to thank the GameLift team for providing excellent support while we built this title. In particular, Mark, Shashil, Juho, Dan, and May. We'd love for you to experience what we helped create. Download Squid Game Unleashed using the QR code on the screen, and visit AWS in the Expo Hall if you have questions for them. And we included a QR code to a GitHub repo that has some great example code that we used. We'd like to thank you for joining us, and we wish you success in building your games. We have some time for questions, and we'll also be outside in the hall if you want to talk a bit more.
Got just a couple minutes for questions, if anybody has any. No? Okay, we'll be hanging, oh, question here? Okay.
You said you had a tight deadline to deliver this for season 2. My question is, if you had more time, would you have made any different decisions? Like, would you still have used GameLift, or did it provide the flexibility that you were looking for?
Okay, so the question was, since we had a tight time frame, if we had more time, would we make different decisions? Well, it's easy to second guess yourself, of course, but having the crucible of time helps kind of really focus on your attention, and so it helped the game in the fact that it helped us really focus on what's critical to ship the game. Of course, we would like to have, if we had more time, we would probably spend more time building more tools around the system. We really just had time to kind of build the core system the hot paths that the players see. We're still iterating on our backend tools to manage this. We're still adding more visibility into all the metrics. Still, okay, which metrics are most important for analyzing our players' experiences? So we're still iterating on that, and we probably will be forever.
I have a question regarding matchmaking. Are you guys thinking of doing matchmaking like, let's say, everybody in this room, or like making it more geocentric, more like same zip code or something? And if you were to take that approach, do you think your bottlenecks will be on the GameLift side to scale to number of users, or do you think it's going to be more around like internal matchmaking rule set?
So the question was about using more like tightly geolocated matchmaking, and then how that would affect where the bottlenecks would be if we did that.
Yeah.
That's not something we really talked about. One of our main drivers for the game is to get as many players into matches as possible. Even with the global footprint we have, some regions are lightly provisioned, so trying to scope that down to like a zip code would probably yield fewer players per match. So that's not something we haven't looked at. I guess that I don't know if there'd be any particular bottlenecks with that. Obviously, you want to make sure you have probably taking more advantage of like edge level servers deployed to if you want to like really low latency for certain regions, if you're trying to focus on that.
Got it. Thank you.
Hi, thank y'all for coming to talk. I had a question about how you defined at scale in terms of testing, and how like rigorous to like fully test the full breadth of like possibilities in terms of like user like playing the game, and like when in the process you would say to like fully like commit to that.
Okay, so the question is about load testing, how I did that, what scale means, and how to factor in your timelines. Like
at scale meaning like a full like lobby, or like a full like estimated batch of users that are expected to be online.
Yeah, so the hardest part of testing this game was actually testing the full game loop from like launching into a match, doing the matchmaking, going all the way through the process, getting them out of the match, and doing that whole core game loop. To do that, we've got an internal tool that lets us essentially scale AWS servers to act as clients. So we just built like a custom Linux build that we deployed to our servers that acted as clients, and depending on the scale of test, there might be thousands of those servers we spin up to act as the test clients. We would then basically try to DDoS our own servers. So
they have full matches attached to them, so it'd be just like the real player experience.
Yeah, so we started doing that maybe 3 months before launch.
Okay.
We did some like closed betas earlier, so we had a basic feel for like a few thousand players, just basic functionality. And then once we had that dialed in, then we started ramping up from there ultimately testing like between 4 or 5 times our expected initial launch time, just to make sure we had lots of headroom. And that extra level of testing helped us give us a lot of confidence when we launched it. So we knew that we can handle multiple times what we expect. So even like worst case scenario, we felt we had it covered, and that played out pretty well. So like Chris said earlier, test early, test often.
Yeah, like test the worst case.
Yes, yeah. Test for the worst case. Build your way up to that. So prove that you can handle a few thousand users, then 10,000 users, and just scale up to there until you exceed your targets.
Thank you.
I think that's all the time we have. All right. Thank you, everyone.